the liquid state. Now, let's see who's been paying attention. Many of you have been around the whole time. If I wanted to show you liquid carbon dioxide, what would I have to do? I'd have to compress it. I'm going to set up an experiment. This is not going to happen immediately, but I'm going to set up an experiment that will let us see liquid carbon dioxide. I have a container that I can put some dry ice in and build up the pressure. So I'm just going to set this up, load it up, and I'll let it sit aside for a while and we'll come back and look at it in a few minutes. It's got a lot of threads on it. There we go. I've got a large test tube. I'm going to pack it with some dry ice. And incidentally, every now and then people are worried that I'm handling dry ice with my hands. It is 109 below zero. I'm very careful not to let it sit in any one spot. You can handle it as long as you juggle it around, but you don't want to let it sit in one spot because you could get frostbite. Now I've got this lid I'm going to put on here. And you've already seen it gives off a lot of gas. I've got a valve I'm going to close off and let a pressure build up in here. And I've got a pressure gauge on there. We'll come back and take a look at that in a minute. But in the meantime, I wanted to show you another interesting property of carbon dioxide. Carbon dioxide is a dense gas. Now, density is a word that we use to describe the property of matter that determines whether things float or sink. And that's really, in the North Carolina curriculum, you start to focus on density usually in 7th and a little more in 8th grade. But most of what you talk about in 7th and 8th grade are solids and liquids that float or sink in water. But I'm going to show you gases also have this property of density, this property of floating and sinking. I'm going to throw some carbon dioxide in some dry ice in my aquarium, and it's going to give off a lot of carbon dioxide, but the problem is it's invisible. You won't be able to see it. So what I'm going to do is use another property of carbon dioxide. I hope I have enough candle left here. The other property that I'm going to use is its ability to put out flames. If you have a fire extinguisher, chances are that has carbon dioxide in it to put flames out. Now I'm going to take 2 candles. One of them I'm going to set on the bottom of my aquarium. The other one I'm going to raise up a little bit. So these flames are not the same height. Now I'm going to throw some dry ice in there. It's going to give off a lot of carbon dioxide, and if that carbon dioxide were just to float away, it might not put out either of the candles. But if it settles down to the bottom, it should fill the aquarium pretty much like pouring water in it. Now if I were to pour water in the aquarium, which candle would go out first? The one that's lower, right, the little one. And let's observe that that's exactly what happens when I put some dry ice in. Now, you won't be able to see the carbon dioxide, but imagine that carbon dioxide is rising in there. And it just rose to that level right there. And it should continue to rise. Hopefully it won't make a liar out of me. Okay, it's almost there. Okay. It just rose to this level even though you can't see it in here, and it's going to continue to fill the aquarium. And I'm going to come back and do something with that carbon dioxide in a minute. But let me talk a little bit while I'm waiting about this property of floating and sinking. I've got a couple of cans of Coca-Cola here. Do they float or sink in water? Float? You think they float? Anybody think they sink? You think they sink? You know, it doesn't matter. Well, they're both full. They're both full. Doesn't matter whether you think they float or you think they sink. I would say you're behaving as a scientist. You're establishing your hypothesis. What's a hypothesis? Anybody know? An educated guess. Well, let me show you how I would try to make an educated guess, not just a random guess. These are cans of Coca-Cola. Well, what is Coca-Cola mostly? It's mostly water. If it was all water, the cans would neither float nor sink in water. They just remain wherever you put them. But we put that mostly water Coca-Cola into an aluminum can. Now, aluminum is a metal. It's a light metal, but it still sinks in water. The can of Coca-Cola the can wants to make the can of Coca-Cola sink. These cans are not brim full. Listen, when I shake them around, can you hear there's something sloshing in there? If these were completely filled, you'd hear nothing when I shake it around. But there's a bubble of gas, probably carbon dioxide because they're carbonated. That bubble wants to make the can float. The can wants to make the can of Coca-Cola sink, and the Coca-Cola inside doesn't make too much difference one way or the other. Let's see what it really does. Okay, establish your hypothesis. Float or sink. And let's do the experiment now. See, this is the scientific principle. Okay, so now you know that it's the can that makes it sink rather than the bubble making it float, unless it's Diet Coke. Now, why would a regular Coke sink and a Diet Coke float? What's the big difference in it? One's red. Well, that's a difference, but that's not the one that makes it float or sink. Sugar. There are 39 grams of sugar in a regular Coke. That's 10 packets of these little packets of sugar. Those little packets of sugar are supposed to be 4 grams each. That would be 40 grams. It's almost 10 packets of sugar to sweeten a 12-ounce regular Coke. There's less than 1/10 of 1 gram of NutraSweet for the Diet Coke. The can wants to make it sink. The bubble wants to make it float. And it's the sugar that makes the difference. And interestingly enough, in the beverage industry, one of the ways that they measure the amount of sweetener that's been added to the beverage is to measure this property that we call density to determine how sweet a beverage is. Now, I also have some soap bubble solution here. Do soap bubbles float or sink in air? After my breath stops stirring around.
Sink.
Gonna sink? Okay. Anybody think they're gonna float? Somebody humor me. Tell me you think they're gonna float. They're just gonna float a little bit, okay? But let me show you how I would establish my hypothesis. These are gonna be air-filled soap bubbles. If they were all air, they'd neither float nor sink. But the walls of the soap bubble are made of soapy water. That should make the bubble heavier, which should make it more dense, which should make it sink. Now, I don't think I introduced myself to anybody here, but my name is Bill Schweitzer. I used to teach chemistry up at NC State University. Everybody knows that university professors are full of hot what? Hot air. And everybody knows hot air rises, right? Right? Hot air rises. Let's see if I really am full of hot air. See, I am not full of hot air, but you know, if I ever get one of my colleagues from UNC Chapel Hill to do the same experiment, those bubbles are going to go right to the ceiling, aren't they? I have very good friends at Chapel Hill, but I cannot resist that joke. Remember, I should have an aquarium that's pretty full of carbon dioxide from the dry ice in there. Dense carbon dioxide. Watch what happens if I can get one of my bubbles to land in there. Those soap bubbles that sink in air do actually float in carbon dioxide. And see if you can see any change in it. Don't hit the wall. It's getting bigger. That's not your imagination. Carbon dioxide can actually flow inside of that bubble, and it's by a process that when you take biology, you'll learn is osmosis. Osmosis is the flow of a fluid across the membrane without breaking it. Well, the fluid is carbon dioxide, the membrane is the wall of the soap bubble, and it's pretty easy to understand with the soap bubble, because carbon dioxide is slightly soluble in water. That's the fizz in our soda pop. When the bubble lands in the aquarium, some of that carbon dioxide dissolves in the walls, but the walls are very thin. It can bubble out on the inside, which inflates the soap bubble, and it also will sink a little bit deeper in there. But really, to prove to you that this is osmosis, I need to prove to you that carbon dioxide is a fluid. Well, a fluid is anything that will slow. Hopefully one of these works. And I want to show you that I can pour carbon dioxide. Anything that flows can be poured. I want to show you that I can pour the carbon dioxide. Watch me scoop up some of that carbon dioxide. Can you see it flowing? You know, sometimes... Oops. Can't have lost the battery. Where'd it go? I can't have lost the battery already. We've replaced it. You know, sometimes, I'm a scientist, sometimes you have to see with your imagination. So let's say, imagine I have a cup of carbon dioxide. I'm going to bring it over here, pour it over my candle, and put the candle out. Okay? All fluids flow. Both liquids and gases are fluids, both will flow. Now let's come back and take a look at my container. This container, incidentally, is a canister that is intended to be used on an air compressor. You can place drying agents in there to try to remove the moisture from the water, because with an air compressor, when you put the air under pressure, that will condense some of the water that's in the air, and with cheap ones like I've used, you just have to valve that you drain the water off periodically. But you can buy air compressors that will allow you to put air drying agents in there to remove the air, and that's what this was. It was intended to contain a little pressure. Now, maybe you should have been worried. I put this in here and I capped it off. How come I wasn't worried about an explosion? There's been some reports in the news really within the last month about people taking pop bottles and packing them with dry ice and putting them in airports and having them explode and really scaring a lot of people. I didn't worry about it exploding because of that device right there, which was bought at Lowe's Home Improvement. This is a pressure release valve. If you have a hot water heater in your home, you have a valve just like that on your hot water heater. If the thermostat fails on your hot water heater and you boil the water, you go from a small volume of liquid to a big volume of gas at a high pressure, and you have a terrible explosion. That's a safety valve that keeps the pressure from ever getting above 85 pounds per square inch. And that's about where we are now. But what I want you to notice is that there is a liquid in here now. We started with dry ice in here. Dry ice does not exist in the liquid state at atmospheric pressure. You guys are among the few people on Earth who have ever seen liquid carbon dioxide. It does not exist at atmospheric pressure. You have to put it under pressure, a pressure of at least 60 pounds per square inch. And what's unusual about dry ice is that it goes from the solid to the gaseous state before it ever gets warm enough to melt. But if you put a liquid under pressure, it boils at a higher temperature. If you were here earlier, I showed you butane exists at room temperature because it's under pressure. You put a solid that sublimes under pressure, and it will sublime at a higher temperature until it finally gets warm enough to melt. Now, if you've condensed the gas to make a liquid by putting it under pressure, all you have to do to make it boil is lower the pressure. What I'm going to do is release the pressure, and you're going to see this liquid carbon dioxide start to boil. Boiling is nothing more than evaporation, and by a phenomenon that we call evaporative cooling, that liquid is going to get colder. Think about it. You have moisture on your hands, sweat on your arm, you blow on it, it feels cooler. That's evaporative cooling. Well, what's going to happen to a liquid if I make it colder? What happens to a liquid? It'll freeze. I'm going to show you this liquid carbon dioxide freezing by boiling. And all I have to do is lower the pressure. See the liquid in there? Look for bubbles first. Bubbles coming off. Solid beginning to form as it freezes. Now you know that it's a solid because it has a shape of its own. So I have shown you now a liquid that freezes by boiling. If you are observant driving around the highways, you will occasionally find a truck that looks like the sort that might carry propane, and it might say on it liquid carbonic. That really is liquid carbon dioxide that is both cold and under pressure. And the way they make dry ice is to pour it out of that container as a liquid because it flows into a mold. And then they lower the pressure and it will freeze itself. No additional refrigeration required. Okay? Well, that's a good place for me to stop. I'm going to go ahead and